can call me Gianni. I'm currently a digital design engineer in ST Microelectronics in Cornaredo, and I'm a former PhD student of the VLSI lab of the Department of Electronics and Telecommunications of Politecnico. As Fabrizio said, I would like, with this talk, to give you an idea which is the link between a doctoral experience and industry. Here you can see the Politecnico entrance, the main entrance of Politecnico, and this is the area of ST Microelectronics in Cornaredo where I work. In particular, I work at the top floor of this building, which is called the Quadrifoglio, since it has that type of shape. Before starting, I would like to do some preliminary acknowledgements. First of all, to the IEEE student branch that gave me the opportunity to give to you this talk. Then I would like also to thank ST Microelectronics and in particular Dr. Marco Castellano, my supervisor, since he gave me the opportunity to give this talk to you. And then I would like for sure to thank the Politecnico di Torino and the VLSI lab, more specific, where I did my PhD. An important premise that I would like to say is this one. I do not give any type of life lesson in this talk. I'm not, so please do not misunderstand this type of talk, because I just want to give you an idea of an experience done during a PhD activity. I do not want to to provide to you any fundamental law, any dogma, and something like that. It's only an experience, a personal experience, nothing more. Well, the presentation will be made of 4 parts. After an introduction to myself, I will talk about quantum computing, and in particular, I will talk about a particular activity that I did during my PhD, which is the classical simulation of quantum technologies based on compact models. Then there is a 3rd part concerning the relationship between the PhD and the industry, and finally I will give to you some conclusions of this experience. Let's start with the introduction. As I said previously, I'm a digital design engineer in the analog MEMS and sensors group R&D group team at ST Microelectronics in Cornaredo, which is close to Milan. I received all my degrees from Politecnico di Torino in electronic engineering. I completed the PhD in July 2022, so less than 5 months ago. As I said previously, my doctoral activities were mainly focused on quantum computing for what concerns the compact modeling of hardware and the quantum compliant approaches to telecommunications industry, as I will briefly explain later. And also I did other activities. In particular, I was the laboratory assistant in 2 courses, digital systems electronics and embedded systems integration. The first one for Bachelor of Science and given by Professor Zamboni, and the other one of Master of Science and given by Professor Suroroc and Turvani. I was the treasurer of the IEEE student branch between 2019 and 2021, and I also had the opportunity to do a research activity in collaboration with Team SAPA, as I said previously, for quantum compliant approaches to telecommunications industry. I currently work in an R&D team, and in particular, which designs digital architectures for chips which are analog on top, so for analog and power applications. In particular, I'm focused on the design of digital receivers employed in the communication between the power receiver and the power transmitter in wireless power transfer systems. I will give to you an idea later in the 3rd part of this talk. And this is, just to give you a brief introduction, this is the block scheme of a demodulator. I will explain it better later. Well, the activity of the PhD, my experience of PhD started after 2 preliminary experiences. The first one was an internship that I did in 2015 at the Istituto Nazionale di Ricerca Metrologica, which is the primary meteorological institute of Italy, which is located in Turin. And in particular, I worked with Professor Costanzo on the design of a proportional integral derivative controller for a PLL which was employed in a geodesy experiment. I was quite young, but it was the first flavor, first taste of what is a research activity. The second activity is the activity concerning my thesis. In my thesis, I worked on the definition of the very first version of a compact model of a quantum technology. In particular, I developed a technology, a model for a technology which is here shown, which is the molecular nanomagnet, which is based on 7 atoms of chromium and 1 atom of nickel. For this reason, it is briefly called CR7 nickel-based molecular nanomagnets. This system globally behaves as a spin-1/2 system that can encode a qubit. I received my degree on April 2018. For this reason, I can substantially say that the first CR7 which arrived in Turin was this molecule and not Cristiano Ronaldo, who arrived in July 2018. For this reason, I would like always to remind this thing to all of you. But in any case, apart from joking, the two experiences convinced me that research suited me, that research could be an important experience. The PhD could be an enriching experience that I should do before going in the world of work to let's say, enhance my skills, my competencies, and also to become more eclectic. And I think that after 3 years and a half, let's say 4 years, I can say that this goal was achieved. I would like to show here some numbers, some of my PhD. Okay, I assisted 10 Master of Science thesis students. I will briefly introduce them later. I did have 8 publications on quantum computing. If I'm not wrong, I presented 7 pitched seminars, which is, maybe no, one of the most famous activity of the IEEE student branch, where PhD students present their activity. And when I was the treasurer, usually the two presenters were me and you were Daisy, who is now here. And we usually alternated in the presentation of this event. 3 students started a PhD on quantum computing after me. For what concerns speech, I would like to remind you that we won the Darrell Chong Bronze Award in 2021 for this type of event. It is a student activity award given by IEEE. Then I won a Kiskit Camp Community Choice Award with two guys of Down, Eduardo Giusto and Mohamed Ghazivaki in 2019. And as written in bold here, I have never designed a digital demultiplexer in my PhD. And as you can see here, this is the region where my mom was born. This exists, but this does not exist. Just to remind again another time. PhD is undoubtedly this. Okay, there are some papers for sure where you can see different titles, but in most of cases, you could receive mails like that. This is, I cut the title, but it is a mail associated with a reject of a research article. These activities are undoubtedly important, are probably the first thing to do during a doctoral activity, because for sure there are some evaluation criteria associated with these publications. We cannot kid ourselves saying that they are not important. But it is important to remind that PhD is not only this, but it is also this. You can see here some pictures of my years as a doctoral student. There are some activities done with the IEEE student branch. Just to precise better, this guy was not a guy of the IEEE student branch. We were having this, taking this picture in close to the high rooms of Politecnico. This guy passed, we had an additional t-shirt, and Umberto Carlando asked to him, can you take a picture? Can you join us for this picture? And he said yes. So this guy is absolutely a random guy that joined this picture. And then for sure there are the parties like this one, and also some moments like this where we joined the end of let's say the proclamation. I don't know if it is a correct word, sincerely, but you understood that it is the degree reception ceremony. Let's say this way. Now, apart from this part, more funny, I would like to give more in the detail with the second part that concerns quantum computing. Well, quantum computing is a discipline of information theory which exploits quantum mechanics for doing calculations. In particular, it exploits some principles of quantum mechanics for doing these operations. I would like to mention here 3 principles. The first one is the superposition. This means that the state of a quantum system is described by a linear combination of the so-called basis states, which are the states in which that system can be measured. In this case, we can see a non-violent description of the Schrödinger's cat, which is in a superposition of awake and asleep states. Before the measurement operation, so when the cat is in the box, the state is described by the superposition of two basis states. After the measurement, which consists in opening the box, we say that the state collapses to only one of the measurable states. In this case, we find the cat alive. Another principle is the entanglement, which is, let's say, a remote interaction, an intrinsic strong interaction between quantum systems, according to which the systems cannot be described independently, but they must necessarily be described together. This mechanism can be useful in some quantum algorithms to accelerate the convergence to the solution of the problem to be solved, or it is also exploited in some quantum communication protocols. Finally, there is the tunneling effect that is suitable in particular with a particular family of quantum computers that are called quantum annealers that are thought for solving optimization problems. In particular, the objective function of the optimization problem is mapped onto the energy profile of a quantum system. And the goal of the quantum annealer is to achieve its ground state corresponding to the optimal solution, and quantum mechanics allows one to exploit the tunneling effect. For this reason, the system can tunnel high and narrow barriers instead of jumping them. This can be useful to accelerate the convergence to the ground state. Here you can see the typical description of the qubit, which is the unit of information of quantum computing. It is described by the superposition of two basis states encoding 0 and 1. Usually the qubit state is described by a complex vector with two numbers, C0 and C1, which are called probability amplitudes. These are two complex numbers whose magnitude square correspond to the value of measuring the qubit in the corresponding basis state. All the states for a single qubit can be described on the block sphere, which is let's say a sphere. It's a sphere, a Cartesian sphere. The two basis states 0 and 1 correspond to the north pole and the south pole respectively of this sphere, and all the states which start in the origin of this Cartesian axis and end on the surface of this sphere are emitted states for the qubit. So there are states where the qubit can be, where the superposition state of the qubit can be effective. For sure, when we do the measurement, the state will collapse to one, to one of the basis states, as I said previously. If we do the measurement along the z-axis, we will have only either 0 or 1. In a system with n qubits, the state vector has 2 to the n probability amplitudes, like shown here. Now, why it is important, this preliminary description? The operations of quantum computer can be seen as unitary matrices that affect the state vector. The system is intrinsically linear, so we can exploit the superposition effects principle that is also employed in circuit theory. For this reason, when we apply an operation, These are usually called quantum gates. The effect on the quantum gate on a superposition system, state system, qubit systems, can be seen as the effect of each operator, of the operator on each basis state independently on the others. Just to give you an idea, here I wrote a very simple demo. We have initially a superposition of these four states, 0, 1, 2, and 3 in binary notation. We add to the qubits associated with this superposition state the value 1, 1 plus 3. So this is the unitary evolution associated with the addition. We can see that after this operation, the superposition states change. And in particular, we have that the value 1, 1, that's 3, was added to each basis state independently of the others. For this reason, 0 became 3, 1 became 4, 2 became 5, and 3 became 6. So this means that quantum computing implements a sort of virtual parallel calculation. The same operation is done on multiple data simultaneously. But this is a huge advantage provided by quantum computation. But it is not sufficient because we did not change the probability distribution of these basis states. We must remind that after the measurement, the state will be only 1. For this reason, in quantum algorithms, what we usually do is to change the probabilities to maximize the probability of a certain state that will correspond to the solution of our problem. Just to give you an additional idea, I prepared a demo where we compare the classical and the quantum version of this very funny game that corresponds in picking the blue ball from a box, a deck, something like that. In the worst case scenario, in the classical case, we must pick each ball, and we must do the check whenever we pick a certain ball. In the worst case scenario, we must pick a number of balls to the total number of balls available in the box. In a quantum case, what we can do? We can create a superposition of states associated with these colors. Here you can see the superposition principle with a visive notation. We can clearly see that we have a unique ball with distinguishable colors, because superposition also implies distinguishability between states. Then we can do a parallel check on the superposition states. So we can check, is the current state blue? And we usually map this check in a sign flip of the probability amplitude. Then, thanks to this sign flip, we can then amplify the probability of this state to maximize the probability of measuring on the output the desired state. This is a very simple representation of the Grover search algorithm, which is one of the most famous quantum algorithms that allows us to find an element in an unsorted database with a quadratic speedup with respect to the classical counterpart. So the total number of iterations is proportional to the square root of the number of the elements in the database. Different technologies have been proposed to build a quantum computer. You can see some of these here. Usually the idea is to encode these on a two-level quantum system. For example, a spin system like in molecular spin qubits, or quantize in artificial atoms, two-level atoms, which are the case of superconducting qubits, where we exploit a nonlinear Halsey circuit that a quantum regime shows a quantization of the electrical quantities of the voltage and current of this system. Independently of the technology, usually the operations on single qubit are done according to the so-called magnetic resonance model. So the idea is to apply an oscillation resonant with the resonance frequency of this two-level system, and this operation allows us to change the state of the spin qubit. These technologies have been proposed more or less in the last 30 years for building a quantum computer. But all of these are currently affected by non-ideality phenomena which do not ensure a reliable execution of a quantum algorithm on a real quantum computer. For example, just to give you a very simple idea, here we can see a gate error. The Hadamard gate, ideally, when applied to the basis state 0, ideally creates an equal uniform superposition of basis states 0 and 1. A real Hadamard gate can have a slightly different probability distributions. Here we have a probability of 0 which is slightly higher than the probability of measuring 1. I would like in particular to mention two non-ideality phenomena which are shown starting from this visive representation of the superposition. The first one is the relaxation, which is the phenomenon according to which the system tends to the ground state. So the disk from colored with distinguishable state becomes colored only with one color. This phenomenon is in quantum computing quite dangerous, but it is substantially exploited in photonics for implementing the stimulated emission. So substantially, the spontaneous emission and stimulated emissions are conceptually based on analogous principle. Then there is decoherence. The decoherence is the phenomenon according to which the distinguishability of superposition is not valid anymore. For this reason, we do not have a disk with different colors, but we have a mixture of all possible colors. For this reason, we have a white disk. These are the two phenomena that mainly characterize quantum technologies. From a mathematical point of view, a state affected by relaxation and decoherence, in general by these non-ideality phenomena, is described by the density matrix, which is a generalization of the state vector that I showed previously. The main diagonal of the density matrix corresponds to the probability distribution of these basis states. Now, after this introduction, I would like to give you an idea of what we did at VLSI Lab in the whole quantum computing ecosystem. We tried to define a sort of quantum tool chain that merges everything together, also exploiting the different competencies of PhD students, of Master of Science students, and so on. We can organize it in 3 steps, 3 blocks, 3 layers. The first one is the definition of quantum compliant models for solving specific problems. This can be done according to the employed quantum computing paradigm with consolidated frameworks and languages for quantum computing. For example, OpenQASM 2.0 is a de facto standard for describing quantum circuits, or there are Python libraries, in this case, for formulating the quadratic unconstrained binary optimization models, which are models suitable for current quantum computers. Usually this formulation that you show here is backend unaware. So we do not consider the typical features of quantum hardware. We do it in a quite abstract way. Then the intermediate step substantially consists in translating the abstract model into an equivalent model which is compliant with the backend to be employed. The first step is the backend. We can organize them in 3 categories. Real quantum computers, simulators which try to estimate the response of a quantum computer with a model, and these simulators can take into account or not take into account the non-ideality phenomena of hardware. And finally, there are hardware or software emulators which try to mimic a noiseless quantum computer to obtain its ideal results. My doctoral activities belonged to the leftmost and rightmost part. In particular, I developed a compact model-based simulator of quantum computers, of quantum computing technologies, and I also worked on the definition of a Kubo model for a telecommunication optimization problem in collaboration with TIM, SAPR. The workflow was more or less the same in both domains, even though they are quite distant from each other. I started from a preliminary investigation of the main features of the 2 domains. Then I tried to define some specific approaches, algorithm, to overcome the dimensions, and finally I did a validation with a reference, which could be available in the state of the art or implemented in parallel to the proposed solution. This check was also important to improve the proposed method. Now I will talk about the simulation of quantum computers and compact models. First of all, we know that quantum computers are nowadays available and accessible via cloud, but usually the total number of available qubits of quantum hardware accessible for free is quite limited, and we are not usually so capable of handling all the degrees of freedom of quantum hardware. For this reason, the development of simulators can help us in estimating the performance of a quantum application on quantum hardware by tuning the degrees of freedom, and it also allows us to compare the same application on different technologies to evaluate which is the best one for a certain type of application. The simulation of quantum systems can be done in two ways. The first approach is to solve complex differential equations like the Lindblad equation, which is a sort of generalization of the Schrödinger equation, or this can be done with fast high-level simulators, which usually exploit some formalisms that are quite abstract from the physics. What we try to do with compact modeling is something in the middle, something which finds a compromise between the two domains. We try to describe the physics doing simple calculations. Now this is a conceptual block scheme of the compact model. The compact model is substantially a black box which provides the response of qubits under the effects of quantum gates and non-ideality phenomena, without solving numerically the Lindblad equation. The compact model can be built for Hamiltonian phenomenological or experimental analysis, and it is thought for being inserted into a simulator of quantum circuits, which contains multiple compact models, each one associated with a specific technology. Here you can see a better zoom of the compact model, which is responsible of generating matrices which update the ideal qubit state vector, which is a reference in our simulation, and the density matrix, which describes the noisy qubits. The compact model is based on four submodules, depending on different degrees of freedom. The four modules are the technology, which describes all the native operations of the quantum technology to be simulated. Then there is a decoherence model, a description of the measurement mechanism of the qubits, which can be affected, for example, by errors or uncertainty in the measurement, for sure. And finally, but however, in the current version, the measurement is ideal, so is not affected by this phenomenon. And finally, there is a description of the manipulation operations, so all the physical parameters associated with the physical operations to be done to update the state of qubits. As I said previously, the compact model generates with the matrices which update the state vector and the density matrix. Where it is located? The compact model is located in a simulator of quantum technologies developed in MATLAB at the VLSI lab. We can see that this simulator is based on three main layers. The bottom one is the physical layer, where the compact models interact with a common simulation infrastructure, where let's say that you should imagine that there is a top class where the compact model is instantiated, and the compact model generates the matrices which update the state vector and the density matrix, which are located in this common simulator. In order to simplify the usage of the simulator, we developed an interface of this simulator with OpenQASM 2.0, which is the language that I discussed previously. In this way, a user can simply write his quantum algorithms in OpenQASM 2.0 and can provide it to the backend. There is a third virtual layer, which is the top one. The most consolidated frameworks for quantum computing, like Qiskit from IBM, Circuit from Google, and so on, usually support the translation of a quantum circuit in OpenQASM 2.0. Since this translation is possible, it is possible to virtually employ the simulator as an additional backend of these frameworks. And this allows us to evaluate the performance of our compact models with quantum circuits associated with application-specific circuits, for example, in data-intensive applications, machine learning, or optimization problems. Because the time is not so much, I will just give you an idea of how the compact model of relaxation and decoherence works. You can see here again the scheme of these two phenomena. We can see here that the box of decoherence depends on 3 degrees of freedom. The timescales of relaxation and decoherence of qubits, which are evaluated experimentally, and they are assumed to be provided to our simulator, together with the duration of the quantum gate to be simulated. These three elements allows us to generate the relaxation matrix and the decoherence matrix, which changes the density matrix. And I would like to show you now how it is possible to build a quantum model, let's say in a phenomenological way. We know from theory that the effect of relaxation and decoherence on single qubit is on the density matrix is this one. We can see that T1 associated with relaxation affects the main diagonal of the density matrix, while the decoherence, the terms of decoherence with their T2 values, time constants, affect the off-diagonal terms. The effect of this phenomena is local on the density matrix. For this reason, we can imagine to write the matrices which affect the density matrix according to the element-by-element product, which is shown here. Just to give you an idea, let's see how it works with decoherence. This is the decoherence matrix of a single qubit, and the effect of the element-by-element product will be to change only the terms on the off-diagonal. If you do the element-by-element product, we can prove that only these terms are affected by this matrix. Something similar takes place also for relaxation. In this case, for sake of simplicity, we try to only to use a relaxation vector, which changes the terms on the main diagonal. The problem is that relaxation is a phenomenon that also changes the probabilities, but the sum of the terms of the main diagonal must be clearly equal to 1, since the sum of all probabilities must be equal to 1. So what we did is to develop an additional algorithm which is responsible of updating the probability distribution under relaxation. Okay, and here there is the algorithm. I will be quite fast. The only thing important to say is that we developed an algorithm that provides a higher probability to states which have a higher number of zeros, since zeros are usually associated with the ground state of the qubit, and we provide a higher probability to states which have a lower relaxation time constant, since their transit must be lower. Here we can see some simulation results obtained with our simulator, with simulator of the SI Lab, and what we effectively proved is that we could entirely replicate the expected response of the experiment that is typically done to compute T1 and T2. In fact, T1 is the time constant of this exponential decay of the probability of the qubit starting from 1 and then going to 0. This T2 is associated with the exponential decay of this envelope. This experiment is called Ramsey fringes. Because of lack of time, I will not go into many details. If you are curious, I can answer to you later. Now, let's go now to PhD in the industry, which is probably the most interesting part for you. My first experience with industry was a research project done with Team SAPR on quantum compliant approaches for problems in telecommunications industry. In particular, and I also worked in a smaller amount on some quantum analysis of quantum communication systems. That experience was important to me since it allowed me to understand the importance of technology readiness. So this means that research must be thought, if possible for sure, to obtain a product in the lowest time possible. For this reason, we can say that this type of research is a sort of research and development activity. This was the first experience still at Politecnico. Now I work, as I said at the beginning, on the design of digital demodulators for wireless power transfer system compliant with the CHI standard. The CHI standard is a standard for wireless power transfer that is employed in many products of consumer electronics. For example, it can be employed for fabricating wireless battery chargers for smartphones. In particular, the communication that I must demodulate is the communication between the power receiver and power transmitter, which can be imagined as the communication that the device to be charged says to the charger to say, please do not charge me anymore. My battery is completely charged, or something like that. This is the type of communication that it is at the basis of my work. Now we'd like to show just a bit more in detail the typical scheme of a wireless power transfer system. This is wireless because here we have properly the free space between these two coils. And in any case, the two coils are put quite close to each other to ensure that a mutual induction is present, and this mutual induction allows the power transfer. So a signal, a sine wave, a signal in the primary coil of the power transmitter will force a signal in the power receiver, which can be then, let's say, filtered with a system which is quite similar to that employed in power supplies. We can see that there are the diode rectifier, then there is the capacitive filter with ripples, and then we can imagine then later there is a voltage regulator to keep the voltage constant. The sinusoidal signal is not here in the primary coil is not properly a sine wave, because it is obtained by filtering with a CL filter as a square wave obtained with PWM. This PWM is generated by square wave signal is properly generated by choosing how to close the switches of this inverter, of this power inverter. The communication from power receiver to power transmitter is implemented with a technique that is called backscatter modulation. This practically means changing the load impedance of the power receiver, and thanks to the interaction of the coils, the variation of the load impedance will change the current or the voltage in the primary coil. This can be seen as experimentally corresponds to a variation of the amplitude of the current and voltage. For this reason, we have effectively a binary amplitude modulation, that is the amplitude shift keying. So what we do is to sample this signal, and then we can process it with a demodulator to obtain the modulating signal. The scalable modulators is based on 4 steps. So we start from sampling the signal from the ADC. Then the first operation is to move information from the bandpass to the baseband. So the idea is to we have initially a signal, a sine wave at a certain carrier, and we usually try to obtain another signal which has a component at low frequency. So this operation can be done with a mixer or employing a rectifier. We know that the mixer operation will generate 2 components, the bit and the image signal. The bit frequency will be at a frequency which is the difference between the carrier, the external carrier, and the frequency of the local oscillator, while the image frequency will be at a frequency which is the sum of the 2 frequencies. So the following operation must be necessarily a low-pass filter to remove the image. The same mechanism is also done with peak detectors, if you remember. So we do initial rectification, and then we do a low-pass filtering to keep only the modulating signal. Usually the low-pass filtering in the digital domain is also accompanied by a decimation of the samples to reduce the data rate of the following blocks. These blocks belong to the so-called high-speed domain, which works at the data rate of the ADC. After the decimation, we have the low-speed domain, which is made of other 2 main blocks. The first one is a DC removal. You know that after this low-pass filtering operation, we usually have a DC. This filter is substantially responsible of moving the signal to around the 0 volt, so the 0 value. This is a very, very simple operation. Finally, this square wave around 0 can be provided to a symbol recovery unit which can be exploited to properly detect the symbol, the bit stream. I know that probably I should draw some examples for each layers. Next time I will be more careful about that. I'm sorry. But to give you another idea, I showed an analog equivalent of this architecture that can be seen in a paper of 2013. The idea is more or less this. Here we have the peak detector. This is a peak detector architecture. The first part is a rectifier with a low-pass filter here, which keeps only the modulating part, even though there are still some unwanted harmonics at this point B. Then, after this voltage follower, we have a programmable low-pass filter which tries to keep a better shape of this square wave. This low-pass filter is then high-pass filtered here, obtain this waveform. You can see that this waveform is around 0, as expected. Then this low high-pass filtered signal is provided to a comparator which reduces the information only to 2 levels, following the evolution of the modulating signal. Then the outcome of this comparator can be provided, for example, to a firmware to do the bit detection. This is more or less what we do at a hardware level, at a digital level. Now, it is clear that ASK demodulators and quantum computing are quite different to each other. We cannot kid ourselves. However, the experience in approaching a new topic was more or less the same in both domains. And I would like to show you my personal flowchart in approaching a new topic that is completely new for me. And this is the flowchart. We start from understanding the causes and the critical issues of the problem to be solved. Then we try to list strategies for overcoming the main issues with their pros and cons. At this point, we should ask to ourselves, can I currently follow a strategy on my own? If the answer is no, it is convenient to ask to an expert. This must be done clearly responsibly, to not disturb the expert significantly. In any case, after asking to the expert, we should clearly study, try, do. Because we must do things. We must study things, we must do things to achieve a final result. And this study, I think that with this study will be agreed by the GOAT of Italian electronics. Finally, we should develop a validation environment and then finally do the validation. After the validation, we could also move back to the first 2 layers, because learning is always something iterative. We must always learn something new. This is a thing that is common in both domains. Then, another element, another issue that I found extremely useful and important in my doctoral experience and in industry is the capability of handling mathematics. Quantum computing is strongly mathematical. For example, this is the appendix of a research article that we wrote last year, that required many mathematics. So this was effectively useful for me. In fact, my first activity in industry was to prove a certain phenomenon. And I proved that phenomenon by doing a compact model and also doing some mathematics. I cannot provide any additional details, unfortunately. So the link, you can see that there is a link, there is a bridge. And finally, I would like to show you some people that probably helped us in doing this link. On the left, we can see Taylor and Maclaurin, because engineers, probably much more than mathematicians and physicists, use the Taylor and Maclaurin series. if you see, if you, at least this is my personal experience. I hope to be wrong. Then we have Stephen Butterworth. Stephen Butterworth is the inventor of the Butterworth filter. He was very famous because he had a very huge capability of handling mathematics and in developing models. If you Google Stephen Butterworth, you can see a very small biography on this engineer which says what I said to you before. And then there is Robert Middlebrook, one of the fathers of power electronics, who proposed the so-called design-oriented analysis methodology, which tries to do analysis of electrical circuits with simple equations, which can also be managed by engineers for doing their designs. These are for reference for me. So I would like to put these pictures to remember these people. Then there are the soft skills. Soft skills must not be neglected. They are quite important, like hard skills. There are okay. I show you different pictures. I would like just to remind some soft skills. For example, finding documents in the state of art, and as you probably some of you will remind, we must be kind readers. If some of you remembers kind readers. Then for sure technical writing, public speaking, interaction with older people and younger people. Here you see, okay, a presentation that I did on something that does not exist. Okay, then trying to manage conflicts. Timing, like Walter Mazzarri will remember to all of you. Preparing slides and making mem. Mem are also important in the industry, with moderation. Before concluding, and now we're quite close to the end, patents. In academia, we are usually more interested in writing scientific articles. Industry is usually more concentrated on patents formulation. For example, especially in R&D teams, writing patents is important because it allows the company to protect the invention with respect to the other customers, other manufacturers of analogous products. For example, in my doctoral courses, I had the opportunity to learn patents with a soft skill course. And I also had another patent experience during my first year of the PhD. If you're asking what is this, this is the patent of Harold Stephen Black, which is the first patent where we see explicitly a negative feedback amplifier. If you go back to, this patent was granted in 1937. I find these schematics very beautiful. And these schematics are based on valve tubes amplifiers, not on transistors. Now, where are the conclusions? I hope, first of all, to not bore you excessively, that my experience can help someone in appreciating the PhD like I appreciated it, but I don't know. I hope that you enjoyed these hours spent together. These conclusions are only visible. They are not written text. Okay, the starting point was this one. This is the Department of Control and Computer Engineering. And when I went to the office of Professor Zamboni in February 2017 for the thesis, he said to me, I do not know anything about quantum computing. This thesis is like finding oil below the Department of Control and Computer Engineering. Now, I would like also just to give you some results with being humble, as I said at the beginning. The first results are that now there are three doctoral students, which do their research on quantum computing at Bielsa Lab and started after me. So it is I'm happy of this because it means that I left something. There are not only, and they are continuing and improving the research that I started in the past years. Then there are other guys to thank. These are all guys who did the thesis with us, with our group, in the last 2 years. This guy is now doing also the PhD, but out of quantum computing. Also, he's doing the PhD in the Netherlands on quantum computing. And all the other guys work in important tech companies. There are also 2 colleagues of mine. These are also other guys who are doing their thesis. They did or doing the thesis in quantum computing at the VSL Lab. And this is all. I'm happy of this because I was alone at the beginning. And then there are other guys that are continuing my work. It's a very big pleasure for me. And then other types of things that I would like to remind you that continued after my PhD are these ones. This is an exercise of mesh scripting that I wrote for a course that I still use sincerely for checking the commands, and I know that also other guys working in the companies already still use this file for writing their bash scripts. This book is the book on quantum computing of Dr. Christine Corbett-Moran that Professor Montrucchio uses for the laboratory sessions of a course for a course on quantum computing. And I'm proud of this because I suggested to him this book. And he also always says to the other guys, this book was suggested by Giovanni Cirillo. So I'm happy of this. And these are the well-known Lab 6 of digital systems electronics. Some of the I invented with Yuri Ardesi, Umberto Garlando, Dragoluccio, some of these exercises. So we can say that some guys completed their bachelor with a work that was invented by us. And this is something that I'm happy of this. Now I conclude just the last acknowledgements to my 3 supervisors, the Professor Maurizio Zamboni, Professor Maria Grazia Graziano, and Professor Giovanna Turbani, who followed me during this doctoral experience and helped me to become who I am today, let's say, to mature with doctoral research. That's all. Thank you for your attention. I hope to not be so boring for all of you. Thank you.